and welcome to the second of 4 seminars on how to prepare for the examination on subject C3 Advanced Surveying. I'm Jean-Claude Tétrault. I'm the CBEPS Registrar, and I will be the moderator for this session. The presenter is Dr. James Secord, professor at the Geodetic and Geomatics Engineering Department at the University of New Brunswick. I'm Jean-Claude Tétrault. I'm the CBEPS Registrar, and I will be the moderator for this session. The presenter is Dr. James Secord, professor at the Geodetic and Geomatics Engineering Department at the University of New Brunswick.
In my listing of the items there, you'll notice there are study guide questions or study questions. The one that is in italics, which is number 12, came up during the session. The other ones had been suggested prior to the holding of the session. Similarly, the questions out of 3 different examinations were also discussed.
James, I have one question.
Okay.
Can we go over all the questions from March 2011? I think they apply to this session or the last.
We can do that, yes.
Okay.
So maybe what we'll do is, if there's nothing else coming directly out of the last session, maybe we'll go through item 2.3, which is focused on instrumentation, testing, and utilization, and then after that we can start looking at the questions of last March.
Okay.
So is there anything else about the last session that anyone would like to bring up?
I don't see anything, James. I think you can proceed.
Okay. So today's session is dealing with instrumentation, testing, and utilization, which has been suggested in the learning outcomes of these particular references, preferably in that order, would be probably the easiest way of following it. The Ruger reference, 1996, is his introduction to the electronic distance measurement, which during our last session some people suggested was difficult to obtain because of its vintage. We will have very shortly the juicy bits available with the other reference items on the CBEPS website. The 2003 publication is one that you can get from the University of New South Wales, and it deals with it deals better with electronic total stations than the references that were listed for 2.2 and also for digital automatic levels. The other references that you see in that list, Franksec and the 2 anonymous ones and the Victoria State Surveyor General's publication, all deal with calibration baselines. And then Strasser and Schwendener deal with the gyro attachment that can be used to determine azimuth. So maybe just a few words of explanation to maybe clarify some of the concepts that won't necessarily be readily apparent, and they don't seem to have been obviously understood in some of the attempts at the examinations. When we talk about using EDM instruments, whether they're standalone or whether they're part of a total station, there are certain characteristics of that particular instrument that have to be known. The major one is the offset between the mechanical centering of the instrument reflector combination and the centers electronically. So if you look in Ruger's 1996 book, he discusses what's referred to as the prism offset, the fact that the electro-optical radiation goes through the air, goes through a piece of glass, and then comes back through the air again. And when it goes through the glass, it's going at a slower speed than when it's going through the air. So it thinks it's measured to a point farther on than if it had been reflected directly off the face of the front face of a plane mirror. So that's the prism offset, and similarly there could be an offset between the electronic center and the manual centering portion of the EDM. So we have a combination of EDM and prism offsets, which are normally referred to as the additive constant, to take the EDM distance and make it into an actual mark-to-mark distance between the two centerings. There are ways of determining it. If you look in some of the plain surveying textbooks, they say, well, if you take 3 points in a line, do the two intermediate distances and the overall distance, you can calculate what the additive constant is. The problem with that is that it's a unique determination, and there's no way of statistically checking what's going on. So if we take simply a linear array of points, which can be created by mounting tribrachs onto tripods and lining them up, we can actually do a least squares estimation using all the possible distances. So for instance, if we had 6 points, we would have 15 possible distances. And the problem then is coming up with the observation equation that would relate these distances to the quantities that we don't know. And the quantities that we don't know are the additive constant and the coordinates along this linear baseline. If we just do it with tribrachs and tripods, we can calculate the additive constant, and we can also have, because of that redundancy in the least squares estimation process, a pretty good idea of statistically how the instrument is operating. Usually we set the overall distance to be a little bit more than what the typical use of the instrument would be, so we have a good idea of its behavior over its working range. And if we go into Ruger's discussion of the design of a baseline, he offers several formulas. And if we look at the ISO specifications for coming up with the variance of a distance, there is a reference to what's referred to as the Heerbrugg formula, which basically gives us a way of calculating the spacing between the points if we were to set out this linear array in a way that would allow us to sample different portions of what's referred to as the unit length. Now, the reason for doing that is that there are certain behaviors of electro-optical distance measuring instruments that are cyclic. They have a cycle that is a function of the modulation wavelength, and they cycle half that wavelength in repetition. And that's referred to, curiously enough, as the cyclic error. The magnitude of the cyclic error is a function of the noise to signal ratio. So the greater the noise to the signal, the greater the amplitude. And this is discussed quite well in Ruger 1996. So this would typically be a problem if you're trying to squeak a long distance out of an EDM with, say, a single prism where the return signal is just at the verge of being able to use it. So we can in an ad hoc manner create a linear array of points using tribrachs lined up on tripods with the spacing that would allow us to follow, say, the Heerbrugg design. And we can estimate then the additive constant with some pretty good statistical information along with it. Some of the other references in this particular section deal with what are referred to as calibration baselines. Now, calibration in the general term is taking a measurement system and comparing it to a standard, where the standard is known better than the system that's being compared, usually by at least one order of magnitude. And this is very obvious in something like calibrating a steel tape, where you have a distance that's known much better than what the tape could measure. You measure that distance with the tape and figure out whether the tape is too long or too short. In the earlier days of EDM measurement, most systems would be with a standard deviation in the order of centimeters. If you were really lucky, by the mid-80s, it would be down to about 5 or 6 millimeters. The Electronic fidelity of the instruments wasn't very good, simply because the diode that generates the frequency would sometimes age and start creating problems. The calibration baselines were created, and they were usually measured by the Geodetic Survey of Canada or some other higher authority to give knowledge of the distances, and they were typically 6 or 7 pillars. Because we had knowledge of the distances, we could then also calculate the scale of the EDM, in addition to doing the additive constant and getting some of these other statistical information about the instrument's behavior.